Okay, we will go over chapter 11, or solutions. Solutions consist of a solvent and a solute. The solvent is the component high in concentration, and the solute is the component low in concentration. Here we can see the difference between a strong electrolyte, a weak electrolyte, and a non-electrolyte. So strong electrolytes dissociate completely in solution, and weak electrolytes dissociate partially. Non-electrolytes do not dissociate at all. Conductivity is high for strong electrolytes, weak for low electrolytes, and none for non-electrolytes. Examples of each of these are strong acids and bases, which dissociate completely in solution, and soluble ionic compounds. We can see weak acids and bases are weak electrolytes because they do not dissociate completely in solutions such as water. And sugar, alcohol, organic compounds do not dissociate at all. Polyatomic ions stay together when dissociating. It's important to revise these polyatomic ions. NH4 plus is ammonium, CH3COO- is acetate, OH- is hydroxide, NO3- is nitrate, NO2- is nitrite, MnO4- is permanganate, Cr2O72- is dichromate, carbonate is CO32-, HCO3- is bicarbonate, PO43- is phosphate, and chlorate is ClO3-. ClO4- is perchlorate, SO4-2- is sulfate, and SO3-2- is sulfite. A good way to remember these is by knowing that 8 here is 4 and ite here is 3. Again, with permanganate, there's 4 oxygens, so anything with 8 can be remembered as 4. Ammonium is, I like to think of that money is a plus. So ammonium has a positive charge. It is one of the only with such. Hydroxide, nitrate, nitrite. We can see again that nitrate has an extra oxygen compared to nitrite, but it does not have 4 oxygens, as I mentioned earlier, which is important to note. Permanganate, dichromate. I like to remember the -2 charge of dichromate by knowing that there's a di in front of it, so there's 2 of them. With carbonate, carbon is a very important molecule for our atmosphere, so it has a -2 charge, or at least that's my way of remembering it. Phosphate is 3-, and one way to remember it is just by remembering that fate can be random, so 3- is quite random compared to the other ones, and this is how I remember them. It's important to note that they do not dissociate. So CO3-2-, carbonate, does not dissociate into carbon and oxygen. It stays as CO3-2-. Dissolution and recrystallization are opposite. So dissolution to recrystallization is the forward reaction, and recrystallization to dissolution is the backwards reaction. But the concentration of dissolved solute remains constant, and the undissolved solute, or the amount of it, also remains constant at equilibrium. Solubility refers to the solubility of a solute in a particular solvent is the maximum concentration that may be achieved under given conditions when a dissolution is at dynamic equilibrium. Again, what I mentioned above is dynamic equilibrium. So it is the most amount of concentration of a solvent that can be dissolved at equilibrium. A saturated solution is the maximum solute that can occur at that temperature and pressure. The solute that is there is equal to solubility. So the solute undissolved and the solute dissolved are going into a backwards and forwards reaction at equilibrium. An additional solute will not dissolve because the maximum is already been dissolved. Unsaturated solutions are solutions containing less solute than an equilibrium amount. Additional solute will dissolve. Saturated supersaturated solutions, meaning more than saturation, is a solute containing more solute than the equilibrium amount. It is unstable and it is in a non-equilibrium state. Moreover, immiscible and miscible solutions exist. Immiscible is 2 mutually insoluble liquids, and they form 2 separate phases. An example of this is oil and water. They do not mix. And miscible, one dissolves in another in all proportions, and they exist in a single phase. They become a homogeneous solution. Like dissolve like. So, if we want to know if something is miscible and will dissolve something else, or just if something will dissolve in a solution, polar solvents will dissolve polar solutes, and nonpolar solvents will dissolve nonpolar solutes. This is because like dissolve like. Solubility, temperature, and pressure. For solids, as solubility increases with temperature, for instance, if you're mixing tea, if you're putting ingredients in water, they will be more soluble when we put it in hot water versus cold water. And pressure has no effect on solid because you cannot compress a solid. As temperature increases, solubility decreases for gas. And as pressure increases, solubility increases. A great diagram for this is illustrated here, where we can see that as pressure is low, the gas solubility is low. As pressure is high, the gas is compressed, leading to a higher gas solubility. Here we can also see what saturated, unsaturated, and supersaturated looks like on a curve. Saturated matches the solubility exactly. Supersaturated is above the curve, and unsaturated is below the curve. Here I want to go over the math for this, quickly over some of the things we might need to know. So molarity is the moles of solute in liters of solution. And molality is the moles of solute with 1 kilogram of solvent. This means just the part that is in high concentration. And this means that a whole thing, including the solute and the solvent. That's important to note. And mole fraction is the moles of solute divided by the moles of solute plus the moles of solvent. When converting between these things, we can assume that 1 milliliter of solution exists. For instance, if we're given a molarity, we can assume that it's all moles of solute divided by 1 liter of solution. Same thing can be done for molality, when we can assume that 1 kilogram of solvent is used. For mole fraction, we assume that X is the moles of solute and 1 minus X is the moles of solvent. Colligative properties, are the properties of a solution that are different than pure solvent. They depend on the number of dissolved particles and not the identity of the thing that is dissolved. For non-electrolytes, the Van 't Hoff factor is just 1. And for electrolytes that dissociate in dissolved water, the Van 't Hoff factor, or I, is the moles of particles in solution divided by moles of formula unit dissolves. And it's important to remember, again, that polyatomic ions do not split in water. For other things, you can just count the subscript. For instance, if it's CO2, we know that it would be 2 oxygens and 1 carbon. So 3 would be the Van 't Hoff factor. Vapor pressure of a non-volatile solution is lower than the vapor pressure of a pure solvent. A non-volatile solution is a solution that cannot evaporate. So, to understand the relationship between vapor pressure, we use here P solution, and we use Raoult's laws. So it's the moles of solvent is I, meaning Van 't Hoff factor, times moles of solute plus moles of solute to get the mole concentration times the vapor pressure of the solvent. If both solvent and solute are volatile, they contribute to the overall pressure of the solution, and basically we get the moles of concentration times pressure for both of those things and add them all together. So vapor pressure of a solution decreases, meaning it's lower, meaning less vapor is formed at the same temperature. Here we can see the relationship between the mole fraction and the vapor pressure. It's important that you know how to examine this graph. We see that the vapor pressure of pure solution is 22 torr, and here the vapor pressure is 75. When it's just that, the mole fraction is 1. Here we can see the mole fraction of solution and use these at the bottom to get the mole fraction of the whole thing. Boiling point elevation is something that occurs again with, like we learned of the colligative properties, where solutions have a higher boiling point and lower freezing point. Basically, here we can see in this graph where the boiling point and freezing point change so that the solution becomes more resistant. Here we see that the boiling point of the solution is higher and the freezing point of the solution is lower than the pure solvent. And a good way to quantify this relationship is by using a boiling pressure of the solution minus the boiling pressure of the solvent, which is the change in temperature. And we can find this out by using I, the Van 't Hoff factor, Kb, which is experimentally determined and we do not know but are given, and M, the molality, because it's lowercase. Again, here we've written that. For freezing point, again, we get the change of temperature by getting the pure solvent minus the solution. This is because the freezing point decreases, making it more resistant to changes. And I is a Van 't Hoff factor. Kf is, again, not something we can determine, but is given to us, and M is a molality. When we multiply those things together, we can get the change in temperature. Osmotic pressure is a opposing pressure required to prevent molecules of solvent going through a semi-permeable membrane. You do not need to know this equation for our course, but osmotic pressure increases for a solution compared to a pure solvent. And that is it for chapter 11.